Okay, I hope that helped. Now let's talk about what are some ways of measuring the reaction rate of a chemical reaction. So the important thing here is that you have to have a an ability to measure the concentration of at least one component in the mixture at many points in time. There are two ways of approaching this. For reactions that are complete in less than 1 hour, we call this a short or a quick or a fast reaction. It is best to use what we're going to call continuous monitoring of the concentration. For reactions that happen over a very long time, we're going to call these slow reactions. What we use is sampling of the mixture at various times. That can be used. So let's talk about the first one, continuous monitoring. We've already spoken about the technique of spectroscopy. This one measures the amount of light of a particular wavelength that is absorbed by one component over time. So you can carry your reaction and essentially do it inside the spectrometer and track the absorption of light over time. Now for reactions in the gas state, or let's say for reactions where you have a particular gas, we can simply measure pressure. Don't forget that the total pressure of a gas mixture is stoichiometrically related to the partial pressures of the gases in the reaction. So let's review a little bit. Let's consider the reaction here that we're showing. This is the decomposition of aqueous hydrogen peroxide into water and oxygen gas. Consider that in this case, one of the products is oxygen gas. And so we can monitor the pressure using an instrument that we sometimes call a manometer. Here's just like a graphic, an illustration of a sketch of the instrument. And there are two scenarios. The one on the left essentially has the gas in a bulb that is connected to a U-shaped column, inside of which is a sample of mercury. If the pressure that we're going to be working at is relatively small, less than atmospheric pressure, we can simply have the U-shaped tube essentially closed at one end and allow the mercury to expand or to move against the vacuum. So as gas is produced, it pushes on the mercury, and we can simply take the difference in height between the two sides of the U-shaped column of mercury directly as the pressure. In this case, we would measure it in millimeters of mercury, which is the same as torr, T-O-R-R. The one on the right is an experiment where the pressure of the gas is going to be higher, and so we leave the tube, the U-shaped tube, open so that it'll allow the mercury to push against atmospheric pressure. That way we can control the pressure a little better. In this case, the height of the column is going to represent the difference between the pressure generated by the gas on the left side and the pressure of the atmosphere on the right side. So whichever method we use, let's say if we apply it here to this reaction, here we are carrying out the reaction. You can see it there on the left in a flask that is connected to this U-shaped column of mercury. And what we have is we've put a ruler underneath so we can measure the difference between the two sides of the column of mercury. Once more, we are going to measure the pressure in millimeters of mercury, or torr. Okay, let's see if you guys remember this. Remember this? Yeah, that's the ideal gas equation, PV equals nRT. Now let's do a minor rearrangement of this equation and bring the volume over to the right. Notice that this puts it in units of N, which is moles, and V, which is liters. So moles per liter is molarity. And so we can convert that ratio there into the molarity of oxygen gas. And if we now rearrange the equation again, we can see that the molarity of the oxygen gas would be the pressure times 1 over RT. Remember that in the reaction, the pressure of oxygen is going to change, but we will carry the reaction at constant temperature, so both R and T, R being the ideal gas constant, are both constant. And so when we measure the rate in terms of the appearance or the change in concentration of oxygen gas, that would be delta O2 over delta T, we can substitute this expression we just derived and write this as 1 over RT. Remember, since R and T are constants, we can take them out of that delta O2 expression. And so we have this constant ratio 1 over RT times delta P, or the change in pressure, per delta T. Many times in some of these reactions, we might use different units, as you'll see on the next slide. So again, let's use this experiment where we're going to measure the change in the pressure of oxygen. And once more, we can see here the reaction where the molecules of hydrogen peroxide on the top are converting into oxygen gas, a double red sphere, and water molecules, stoichiometrically adjusted, and this is what the curve looks like. Notice that in this case, once more, we're generating a curve. So what we'll do is, like we did before, we will take the slope of the tangent at each one of these points. I'm only showing you one right now, and calculate what is the instantaneous rate. Notice a couple of things. In this case, we are just measuring the change in pressure in millimeters of mercury, and the time we're measuring in minutes because it's a bit of a slower reaction, and so we have used minutes instead of seconds. Now, you might say, well, didn't we say we're going to measure it in molarity change per second? Well, I'm sure we can change that, right? If you wanted to, you could change the minutes into seconds, and I'm going to leave you a challenge. How would you change delta P into delta molarity of oxygen? I'm going to let you guys do that, but if you have questions, you can always ask me during my office time, okay? I'll leave that up to you because I know you guys can do it. All right. Now, what about reactions that are slower? So in this case, what we do is, rather than continuously monitor the reaction, we will sample the reaction mixture at specific times. A sample from a reaction mixture, we use the word aliquot. So we have aliquots drawn off at specific times during the reaction, and then quantitative analysis is performed. One possible way of doing it is titration for one of the components. You should be familiar with titration from your Chem 1A course, but don't worry, we're going to get some practice with that later in the semester. There's also gravimetric analysis. I hope you remember what that is. If you don't, it means essentially you take one of the components, you precipitate it, and either filter or centrifuge the mixture and weight the amount of that substance via the precipitate that it forms. Another interesting method is gas chromatography. This is when we have various gas components in the mixture, and we can use this technique called gas chromatography. Let me show you how that looks. So in this case, what we'll do is, and again, this is a sketch, all right? We have on the top, you see your sample, your aliquot is going to be injected into the machine. And then we're going to open a valve that is going to cause a carrier gas to push the mixture. The carrier gas will typically be an inert gas, one of the noble gases. But what it'll do is it'll generate a positive pressure that will essentially push the gases in our sample into this spiral column here. Now, two things that you might remember from Chem 1A. One of them is that gases travel at different speeds depending on their relative molecular sizes. The other one is that substances have different affinities if you present them with a stationary phase or a fixed surface, in this case, the material in the column. So as your sample of gases travels through the spiral column, it allows for separation of the gases in the mixture. So when they emerge through, there's a detector that basically quantifies how much of each gas is coming out. And then you generate a graph. You can see it there on the right. We call that a chromatogram. And by running different standards, we can identify which of the standards our samples match. And that's how we run what is called a gas chromatography experiment. Okay? So we have been able to see here different methods, and hopefully you can go back and write down, take notes of what are some of the methods that we have described for studying the rate of reactions, which is essentially the change in the concentration, or if it's gases, the pressure of a particular component. It could be either a reactant or it could be a product. Now, remember, the chemical equation itself has an issue, and that is that we have to deal with the stoichiometry. In other words, the relative ratios of reactants and products in the balanced chemical equation. So let's consider this reaction where reactant A is converted to product B, but in this case, we have 2 units of A converted into 1 unit of B. So we could say that 2 moles of A disappear, so to speak, for each mole of B that is formed. So going back to the rate expression, we said if we are measuring the appearance of product B, let's say the method that we have is able to detect how B is formed, we would say the rate, again, like before, would be delta B over delta T. Now, what if we want to measure the disappearance of reactant A? Remember, we have to convert the rate, the change in molarity of A into a negative value so that both rates will be equalized, right? But in this case, remember, since 2 moles of A disappear for each mole of B, that means that the rate at which B is formed is half of the rate at which A disappears. And to show that, we're going to use a fraction here. We're going to say that the rate is going to be minus 1/2 of the change in A per change in time. So let's consider that. If you want to pause the video now and think about it a little bit, work through the math, see why that is. But let me show you what the expressions are for a generic equation. In this generic equation, the capital A, B represent the product formulas. Capital C and D represent, capital A and B represent the reactants formulas. Capital C and D represent the product formulas. And the lowercase letters A, B, C, D represent the stoichiometric coefficients. So to get a rate expression here based on any one of those components, we can start by saying, for example, that if the rate is measured in terms of the disappearance of reactant A, we're going to have to adjust the rate expression by minus 1 over the stoichiometric coefficient, which is A. In the case of B, that would be, right, minus 1 over B times the change in B over T. If we want to measure it in terms of products, that would be 1 over C times delta C over delta T, or 1 over D times delta D over delta T. Notice that when we do the experiment, we are actually measuring the change in concentration of a product or a reactant. So in other words, we may be measuring simply what is the rate at which C appears. This adjustment here with the reciprocals of stoichiometric coefficients is done so that we can get an expression of the rate that is consistent for each one of these. And many times the way we use this is as we will use it in some of the next practice exercises. Okay, so let's first of all practice with a real reaction here. This is, of course, you recognize it as the combustion of CH4, which is methane, the fuel that we use in our Bunsen burners in the lab. So we have the reaction here with CH4, oxygen, and the products are CO2 and water. The equation is already balanced. So what would be the rate expression for this reaction in terms of every one of the components of it? Of course, if we start with methane, we would say that the rate would be minus the change in methane over time. Now, if we want to equalize that to the rate of disappearance or consumption of oxygen, we have to take into account that stoichiometric coefficient there. In other words, oxygen disappears at twice the rate that CH4 does. So if we want to equalize the rate expression, we're going to have to put a minus 1/2 factor in here times the change in oxygen over time. Now, if we are measuring the appearance of CO2, then simply the rate expression would be delta CO2 over delta T. That is already positive because CO2 would be increasing and therefore delta CO2 would be positive already. However, if our measurement is going to be to detect the appearance or production of H2O, of water, take into account that there is a coefficient of 2 in here. And so when we write the rate expression, we're going to have to put a factor again of 1/2 times the change in concentration of water over time. Okay? So let me give you a few seconds for you to take care of that. Make sure you understand it. Again, you can just pause the video and come back as soon as you're finished with that. And we're going to do a practice exercise now. So we're going to consider this reaction. All right, here we have pH3 being converted into P4 and hydrogen. Please look at the equation, look at the stoichiometric coefficients. You might want to think, how would we more or less be measuring the change in these different components, right? Think about what method you think would be useful. Spectroscopy, titration, gas chromatography, I don't know. Just think about it for a moment. Now, let's say that whatever the method is, let's suppose at a particular moment during the reaction, molecular hydrogen, that's H2, is being formed at the rate of 0.078 molar units per second. Question A, at what rate is P4 being formed? Question B, at what rate is pH3 reacting? Right? So let's go ahead and go into our document camera here, and we're going to solve this one by hand. And we'll be back to wrap up our discussion. Okay, students, let's tackle this problem here that you have in your handout. The first thing that you have to do when you solve a problem like this is understand, what does this mean? What is this data they're giving you here? What is that number? It says hydrogen is being formed at the rate of 0.078 molar units per second. In other words, this is essentially delta H2 over delta T. Okay, so it's important we always read what they give us and kind of interpret it in terms of what we're looking for. So let's start out by saying, well, at what rate is P4 being formed? It might help for us to go ahead and write out what are the various rate expressions for this equation here. So remember that a rate expression allows us to compare the rate of change of one component with the relative rates of change of the other components. So we could express this in this equation as follows. We can say that this is going to be minus 1/4 of the change in pH3 over delta T, or we could say it's going to be the change in the molarity of P4 over delta T, or we can say that it's going to be 1/6 of the change in the molarity of H2 over delta T. So it helps to have the whole thing there in one kind of like image, in one frame, so we can help ourselves. Okay, so the first question is, at what rate is P4 being formed? In other words, what is delta P4 over delta T? Since the only information they're providing us is the change in hydrogen, well, we have to therefore compare the rate of P4 formation with the rate of hydrogen formation according to the equation and according to these expressions we've set. So we said that delta P4 over delta T equals 1/6 times, delta H2 over delta T, right? That's what this rate expression is. In other words, this would be 1/6 times 0.078 molar units per second, right? That's what the data they give us is. And so we can simply solve that, and we can say that the rate of change of P4, in other words, P4 is being formed at a rate, when we solve this, of approximately about 0.013 molar units per second. Okay? If you want to pause the video and work that yourselves, get your calculator out, you can probably do it in your head, but hey, go ahead and use your calculator. Don't be ashamed of that. You don't have to do things in your head. Don't worry. Now, the second question is a little more interesting. This one is asking us, at what rate is pH3 changing? Now, we have now two of these guys. We have the rate of change of hydrogen, and we have the rate of change of P4. So we could use either one of those to find out what is pH3. So what I want to do is, make my life a little simple. Let me compare the disappearance of pH3 with the formation of P4, because the formation of P4 doesn't have any extra coefficients in there. So I'm going to make my life a little simple here. I'm going to say, since I already established that the rate at which P4 is being formed is 0.013 molar units per second, according to the rate expression I just derived here, this should be minus 1/4 times the change in pH3 concentration over time. See? And so what I'm going to do now is I'm simply going to solve for this equation. Now it says, at what rate is pH3 reacting? So since I know pH3 is reacting, I'm simply going to leave the negative sign with it. Again, it's up to you. You can either leave the negative sign, or you can take it out and then in words explain, pH3 is being consumed, is reacting. So I'm going to say that minus the change in pH3 over time would be, I'm going to solve this here, 4 times 0.013 molar units per second, which equals 0.052 molar units per second. And again, like I said, you can use it both ways. The convention is then, since we already know that pH3 is decreasing, so we say, well, minus the change there is the decrease, and it's decreasing at a rate of 0.052 molar units per second. Again, remember, the rate expression allows me to convert between the rates of different reactants or products. In other words, it's a way of kind of like evening out the field. But what we measure in the lab is the actual delta of concentration of any one component divided over the time. Okay, so I hope that helps, and we're sure up. Thank you so much. Okay, students, that concludes the first section of our study of chemical kinetics. Please make sure that you go back to your Canvas page, and where these videos are embedded, please make sure you look at some of the skills or objectives that we want you to achieve with this section. In our next section, we're going to talk about something called rate laws. So I'll see you then. Thank you so much.